Hello everybody, my name's Chris Brady, author of the Boeing 737 Technical Guide and the Boeing 737 Tech Site. And this presentation is all about the air conditioning system on the 737. So by way of scope and disclaimer, I say this is about the air conditioning system on all models of the 737. Now in the FCOMs, the air conditioning, pneumatics and pressurization have all been rolled into one under the title of air systems. What I've done here is I've broken them out into those three individual parts. If you haven't already watched my pneumatics presentation, I suggest that you watch that first, and then this one, and then the pressurization one is the last in the trilogy, if you like. My usual disclaimer, please always treat your company training and manuals as the authoritative source of information. Okay, so by way of overview, this schematic you'll remember from the pneumatics presentation. I've omitted the engine bleed side of things on here just to simplify things, but this is the area of the schematic that we'll be looking at in this presentation. So, as a high-level summary, there are two air conditioning packs, and these use bleed air from the engines or the APU. Inside the packs, bleed air is cooled by ram air through heat exchangers and an air cycle machine. A water separator collects water condensed by the cooling process to avoid icing. That air then flows to the mixed manifold for onward distribution to the rest of the cabin. Okay, so let's take a look at this in a bit more detail. The two air conditioning packs are located underneath the aircraft in the locations I've marked there in the red outline. Those packs are accessed through those two large access panels that sit between the ram air inlet and the wheel well. Opening at either of those panels, you will see this. That is the air conditioning pack itself. This bay is known as the air conditioning compartment, and this particular one that I've photographed here is that for short-bodied aircraft. Now, I'll be making frequent references and differentiation between short-bodied aircraft and long-bodied aircraft. So the short bodies are the 1, 2, 3, 5, 6 and 700 series, so that's spanning originals to NGs. The long bodies are the 4, 8, 9 and all of the MAX series, and they've got two quite different air conditioning systems. So for brevity, we're just going to refer to them as short body and long body. Okay, so the first component I've got highlighted there is the water separator, and that's simply a centrifuge which just flings the particles of water to the outside of that tube for collection. That is the famous air cycle machine that you see on schematics, and you can see that's got two, a compressor and a turbine stage there on either side of it. You've got a primary heat exchanger and a secondary heat exchanger. Okay, on the long-bodied aircraft, there are some differences. So, the first item I've got highlighted there is the reheater, and that is the condenser. Surrounding the condenser, there are two water extractors, and those three, 4 units, depending how you count them. All those units in the light colour that I've highlighted so far, that is all collectively known as the high pressure water extractor, and it all takes the same role as the water separator in the previous photograph. So the rest of the components are just the same. We've got an air cycle machine there, primary heat exchanger and secondary heat exchanger. What you can also see on this photo that you couldn't on the others is the ram air exhaust louver, that's simply because of the angle that I took this photograph at. So the airflow, you've probably traced it out on the schematic in the FCOM, maybe on the schematic which I've provided in my book and in the other presentation. Now, as you probably know, I'm a kind of visual photograph sort of guy. I find a picture speaks 1,000 words, and if I can visualize the things, it makes it a little bit easier for me to comprehend. So for those of you that think the same way, this slide is for you. The rest of you, I guess, can skip on, but it's probably worth a look. So the air conditioning flow starts, well, obviously it starts at the pack valve, but after the pack valve, the first place it goes is to the primary heat exchanger, which is marked with that circle. From there, it goes up to the air cycle machine, particularly the compressor stage of the air cycle machine. So it's from the compressor heats the air. It then goes back through the secondary heat exchanger, because the heated air will be more efficient cooling in the heat exchanger. From the secondary heat exchanger, it goes up to the reheater. Now the reheater, kind of a misnomer at this stage. It has two functions. The air passes twice through the reheater. This first stage is actually a pre-cooler. So from there, it goes across to the condenser, which, as the name would suggest, is where the air is cooled and the water droplets start to condense out of it. The air then splits left and right. I've just shown one side here to keep the diagram simple, into one of the two water extractors. Now, these again are simply centrifuges. A vortex of the air is set up, and the centripetal force flings the heavier water droplets to the outside, where it drips down and is collected. Now, if you just see at the tip of that last arrow, at the bottom of the water extractors, there are actually two tubes coming out of each water extractor. Those tubes take the excess water out. Now, that water isn't wasted. Boeing cleverly designed this so that the water is then taken, and at the end of those pipes, there are actually, on the end of each pipe is a nozzle, and that nozzle feeds into the ram airflow. That ram airflow causes that water to evaporate, and in doing so, it cools the air. So Boeing have cleverly used that excess water from the water extractors to further cool the ram air flow, which is particularly useful on the ground, where the ambient air might be quite warm. Okay, so from the water extractors, the airflow comes around again to the reheater, which this time does work as a reheater, into the turbine stage of the air cycle machine, and off up towards the mixed manifold. So that there, what I've drawn on this photograph, is the airflow in the air conditioning packs. I say this particular one I've drawn it on is the long body aircraft, because it's slightly more complicated than the short body, which was just straight through. Okay, quick word about pack failures. If one pack fails with the pack switches in auto, then the other pack will regulate to high flow. That is, unless the flaps are down. The system assumes that when the flaps are down, you need maximum performance. So it doesn't want to erode that performance by kicking a pack into high flow. The originals, the 1200 series, they didn't have an auto mode. The pack switches were simply on off, so that function that I just described wasn't there with the originals. Okay, quick word about the ground use of the air conditioning packs. Those of us that flew originals and classics will remember that there was an instruction that we're to only use one pack from the APU. Now, this is because the packs are working hardest when delivering cold air, and it's assumed on the ground you'd be wanting that cold air. And the APU isn't on the originals and classics, was not up to the job of powering both air conditioning packs. On the NG and the Max, the APU is much more powerful, so you can use both packs for cooling or heating from the APU. And in actual fact, using both packs on the NG and the Max will cause the APU to burn slightly less fuel than single pack operation. So it's actually recommended that you use both packs with the NG and the Max. Now, for those that might find that a little difficult to comprehend after years of being told to do it one way to now do it the other way, as did I, then what I've got here are 3 photographs I took of the CDU on the APU byte test pages. Now, the top photograph is with both packs off. The center photograph is with one pack on, and the bottom is with both packs on. And I will talk you through the differences here now. So, for a single pack must work harder than 2 packs to cool the cabin to a given temperature. That, I think, we can all understand. If you're only using 1 pack to cool the cabin rather than 2, that 1 pack has got to do much more work. If that pack's got to do much more work, the APU must supply it a higher bleed air pressure, and that you can see on the total pressure fields, which I've highlighted in the red ovals there. So with both packs off, you're around about 19-20 psi. With a single pack, you're up at 58. But both packs, that bleed air pressure is down to 33 psi. So you can see there clearly there's less bleed air pressure with both packs than with one. Now, a higher bleed air pressure requires a greater IGV, inlet guide vein open position than that required for a 2-pack operation. That you can see again there on the highlighted fields. Single pack, the IGVs are driven to about 77-78 degrees. Both packs, it's only 44 degrees. Now, since there's less airflow required to operate 1 pack, a significant amount of unused bleed air is exhausted through the surge control valve, and this actually increases the overall APU generated noise by 2 decibels. So it's actually louder as well, single pack, than both packs. Anyway, getting back to the IGVs, the higher IGV open position and the large quantity of unused air, it translates into a higher APU fuel burn, a higher EGT and higher noise levels for 1-pack operation compared to 2-pack. And you can see that there on the fuel flows, 180 pounds per hour compared to 240 and 204. Okay, ram air. Let's talk about that for a moment. First thing to say is that ram air is not taken into the cabin. It simply is used to cool the bleed air via the primary and secondary heat exchangers, and that what I've drawn on there is the flow of the ram air. The ram air intake, it's kind of composed of 2 or 3 parts. The first part here are the ram air doors. Now these are of variable geometry and that geometry changes as required to regulate the airflow. So if maximum airflow is required, those doors are pretty much full open. As less cooling airflow is required, the doors gradually close. You can see, particularly on the photograph in the top right there of the Classics, there are several hinges on those ram air doors. The deflector doors are something different. They don't actually affect the air intake greatly. Their primary function are simply to reduce any, well, the FCOMs actually say slush ingestion, but it's also any FOD, any foreign object damage ingestion, whatever it might be, any bits and pieces. We don't want those flowing into the into this ram air intake, and that's what the deflector doors do. The shape of the ram air scoops has changed actually with each generation, because there was a further change on the Max as well, as aerodynamic improvements have been made. So the ram air flows, we've already spoken about the variable geometry inlet doors, but on the 737NG, particularly those with the performance improvement package, they've also got variable exhaust louvers. The louvered exhaust doors were there on the classics, but they weren't variable. They were just free flowing in the airflow. The photograph at the top is actually of a classic, showing those free moving doors. The picture at the bottom is of a 737NG, and that was what it was like during most of the NG's life. But as I say, when the performance improvement package was brought in, Boeing went back to those louvered doors, but instead of having them free moving in the airflow, they were actually controlled. The system would set the position of those louvers, and the benefit of that is that when there's less or no cooling required, in flight, those louvers would actually close flush, and that will reduce drag. On the classics, you've also got a turbofan in each side as well to assist with the ram airflow on the ground, and in flight with the flaps extended. Maximum ram air is available on the ground and on takeoff. The ram air door lights, or ram air door full open lights, these should be illuminated on the ground and should extinguish during the climb. If they don't, then all that means is that the cabin's still very hot, and the packs are still demanding full ram airflow for cooling. If the cabin isn't hot and it's been a while since you got airborne, then it's quite possible that the heat exchanger may be faulty. These ram door full open lights have actually been removed on the Max. I'm not sure of the logic behind that, but Boeing obviously thought them superfluous to requirements, and they've now gone. So, a word on temperature control, dealing first with the short body aircraft. So, the short bodies, which were the original setup on the 737, these have got 2-zone temperature controllers, and on these aircraft, the pack output temperatures are independently controlled. So the left temperature controller controls directly the left pack temperature, and the right one the right pack output temperature. In auto mode, which is with the, as you see it there, with the temperature selector knobs in the upper hemisphere of the circle, the pack temperature is controlled by an automatic temperature controller, and this compares the selected temperature on those two knobs with the actual sensed cabin temperature. In manual mode, which is in the bottom half, when you turn those knobs through 180 degrees, your temperature selectors are actually directly driving the hot and cold air mix valves, and that is partially why you've got the air mix valve position indicators up at the top of this panel. Pack problems for short-bodied aircraft. Any pack problems that you will see will illuminate the pack trip-off light. The pack trip-off light means that a pack temperature has exceeded a limit. Now, I've not written on here what that temperature or limit is, because there are 3 temperature pickups around the pack. If you're interested in what they are, they're actually written on the schematic that I've drawn on the opening slide with the figures. You don't need to know them; they're kind of more on there out of interest. But it's worth saying that this temperature is the pack temperature, not the output temperature. It's quite different. The pack temperature is a function of how hard the pack is working, and the packs work hardest when they are cooling. So actually, if the output temperature is very low, the pack temperature is likely to be very high. So with that knowledge, you can see that the remedy for a pack trip-off would actually be to select a warmer temperature to make the pack work less hard. Then after a minute or so's cooling, press the trip reset, and bingo, you should have your packs back available to you. Temperature control on the long body aircraft is quite different. So the cabins or the aircraft divided into 3 zones: the control cabin, forward, and the aft cabin. And the 2 packs actually work to the same temperature, unlike the short bodies where they work independently to whatever temperature you set on the temperature selectors. On this system, both packs work to the same temperature, and that temperature is the coldest of the 3 zones. The other 2 zones, which you require to be warmer, have the warm air introduced by the trim air system, and that goes in after the mixed manifold. Worth mentioning here, I guess, that flight deck air is taken from before the mixed manifold on all series of aircraft. But long-bodied aircraft flight deck air may also contain trim air. So pack problems with the long-bodied aircraft. So on these you've got 2 electronic pack temperature controllers instead of just 1, and as a way of differentiating between the 2 systems, these lights are labelled pack instead of pack trip-off, and this is really to highlight that they have slightly different functionality. So the pack light can illuminate again because the pack temperature has exceeded a limit. That's exactly the same as the short body case, but the extra functionality on these is that it could indicate a failure of the primary and or the standby pack controllers. Now the logic for this is the same with all dual channel systems on the 737. If it's a single failure, then you will only get the pack light illuminating on recall, on master caution recall. If both fail, then the pack light will illuminate as soon as the second one fails. The remedy, well, if it's just that the pack temperature has exceeded a limit, then again select a warmer temperature and press the trip reset. If a pack controller has failed, there's nothing you can do about it with a trip reset. That won't work. That's put it in the tech log and get the engineers to sort that out on the ground. One subtlety of the long body temperature controls is the off position. I wouldn't mind betting that there are many pilots who have long since forgotten that the off position even existed. So just as a little reminder to everybody, well, first of all, they do have an off position, but what does it actually do? If you turn an individual temperature selector to the off position, it will shut off the trimmer to that particular zone. So it's an individual version of the trimmer switch above. The trimmer on-off switch above switches on or off trimmer to all of the zones, or certainly to the 2 active zones. It switches off the whole trimmer system. But you can, if you so wish, and I really can't think of a situation why you would need to do this, but you can switch off the trimmer to an individual zone. Point of interest: if all temperature selectors are switched off, then the left pack will target 24 centigrade and the right pack will target 18 centigrade. Very quick word of temperature control on the originals. The system was exactly the same as the short body, with the sole exception that the panel allowed you to interrogate the left and right pack temperatures as well. With the BBJs, and this is in particular the BBJ1s, so the short body BBJs, these have got effectively a hybrid system between the short and long body, and the reason for this is because the cabin is often divided in these aircraft for privacy. So there was a greater degree of temperature control required, and this photo shows a panel with the retrofit done by Raytheon, and you can see that we've got the 3-zone temperatures controllers of the long body. We've got the mixed valve positions of the short body, and up at the top right we've got trim air and zone control switches that again you would only see on long body. So it really is a hybrid system. Cabin temperature is sensed here. You probably all familiar with the picture at the top right, and those of you who haven't seen it yet, it's on the right hand side of the aircraft at around about row 3, just over the overhead locker. The picture below, I would imagine less of you have seen, and you can see by the arrow that I'm pointing to what is behind the grille. So the first thing that is behind this grille is a piece of foam, a filter, and you find that if the temperature controls are not working particularly well on the aircraft, get an engineer in, mention it to him, and a pound to a pinch, one of the first things he will do is he will just, with a screwdriver, nip off that cover, take the foam filter out, give it a blow, give it a wash, dry it out, put it back in. Job done. And that fixes most of the problems. The rest of that unit, working to the left there, is the actual temperature probe itself. And then where it turns red, and that cylindrical unit on the left, that is a fan. And that's there to draw air through that grill and across the thermometer. If that fan wasn't there, then that air would stagnate and probably get hot, and the temperature control would be useless in the cabin. So it needs an airflow over it, and that's what that fan does. If you're down the back on a turnaround, so the cabin's quite quiet, if you put your ear to the overhead locker round about row 3, you can hear this whirring away just gently in the background. Okay, so the mixed manifold, if you recall from the schematic here, it takes its air from the packs, the recirc fans, and ground air if it's in use, and mixes it before distribution to the cabin. Again, let me just reiterate that the flight deck does not get air from the mixed manifold. Flight deck air is separate, it's straight from the left pack. And here is what that mixed manifold looks like. This photograph I took when the panel was removed, so you can see all of the workings. This is looking into the forward hold of a 737, looking to the back wall of the forward hold. So the area that you're looking at is in between the forward hold and the wheel well, and it's known as the distribution compartment. And as I say, that large brown coloured dustbin type thing, that is your mixed manifold. Above it is the distribution manifold, so that's where the air is taken away out to the sidewall risers for the cabin. These two units are your recirc fans. That's what they actually look like. These two are trimmer mufflers, so you know, just looks exactly the same to me as an exhaust pipe on a car, and the mufflers do exactly the same function. They keep the noise levels down. So the flow of air throughout that distribution area is as follows. Starting from the bottom, you've got air coming in from the left and right hand packs. Air also coming in from the left and right recirc fans. I haven't drawn it, but if ground conditioned air was in use, that actually comes up straight from the bottom, and it's all mixed in this mixed manifold. Then out at the top to the left and right sidewall risers. You can see the trimmer does not feed directly into the mixed manifold, it actually feeds into the individual risers, and the same is true of the one at the back that's partially hidden. So where are those sidewall risers? For those of you that don't know, they you can see their location externally because it's where the passenger windows are blanked off. So if you look at these three photos, you can see that short-bodied aircraft have one sidewall riser on each side of the fuselage. And you see I've highlighted the single missing window there on the left-hand side. Long bodies, though, have got two sidewall risers on the left-hand side and one on the right-hand side. The flow from these is as follows. The left riser on the short bodies feeds the forward cabin. The forward left riser on the long bodies also feeds the forward cabin. The aft left riser goes to the aft cabin, and the right hand riser on all 737 short and long bodies goes back to the aft cabin. So that's how the air flows throughout the cabin. Air for flight deck is taken from the left pack via a duct near the keel beam, and I've shown it on there. Air for the cabin, as we've seen, comes from the mixed manifold up the 2 or 3 sidewall risers along the top of the cabin for distribution. Okay, so let me have a quick word with you about ventilation rates, and this is actually quite topical. In the last week in March, the MAX 8200 was certified by the FAA, and the document that was issued was the type certificate data sheet, and that's a public document. You can go search for it, or you can find it on my website. But what I've done is I've highlighted an extract of it here at the top right of the page. And what it shows is 3 maximum seating capacities for the 8200: 189, 210, and 212 seats, depending on the door arrangements and whether the extra door is used as a Type 2 or Type 3 exit. Now, I'd imagine most of you would be surprised to see figures over 200. Because the headline passenger figure for an 8200 is 200, hence the name. But I draw your attention to the asterisk after the 210 and the 212, and the limitation is main cabin occupancy is limited to 207 passengers and cabin crew members. So it's less than 207 passengers because you need a certain number of cabin crew, excluding flight deck, due to the environmental control system ventilation rate per occupant as defined by 14 CFR 25831A. So if you look down to the bottom right there, you can see I found CFR 25831 section A, and it says for normal operating conditions the ventilation system must be designed to provide each occupant with an airflow containing at least 0.55 pounds of fresh air per minute. Okay, so what does that mean in numbers? 0.55 pounds of fresh air per minute. If you do the maths, if you reverse engineer your 207, it comes out to 1400 cubic feet per minute of fresh air. And this is, I'm sure you'll agree, a heck of a lot. And it's, you know, again, in these times of COVID, probably worth, you know, some comfort to people that there is such a high volume of air, of fresh air required every minute. I mean, 1400 cubic feet is a lot of air. And in fact, the air in the 737 is actually completely changed every couple of minutes. The total ventilation rate is further increased by 25 to 50% using recirculated air. Unfortunately, that doesn't go toward the certification limit, as it's not fresh air, it's recirc air. The MAX 9, which, as you can see above the highlighted section on the right there, you can see it's got passenger figures of 215 and 220. That achieves the requirements by allowing the packs to take more bleed air. So that's how it gets the fresh air requirement. So the total ventilation rate of the short body classics about 1900 cubic feet per minute, or 13 cubic feet per minute per passenger. I think from memory on the originals it was about 1600 cubic feet per minute. Now, when the larger 400 was designed, an extra recirc fan, which has since carried over to the 8 and 900, was installed to increase the ventilation rate to 2100 cubic feet per minute, and this was to increase passenger comfort and help meet the regulation for increased passenger capacity. The ventilation rate of the NGs was further increased by 300 cubic feet per minute over the equivalent classics, and all of the figures I've quoted above there, the 1900 and the 2100, they all include at least 1440 cubic feet per minute of fresh air as required by the regulation. So a word on recirc fans then. They, as we've already seen, they draw cabin air back into the mixed manifold, but importantly that air passes through a HEPA filter. For those who don't know, HEPA filters are hospital grade air filters. These can extract particles down to the bacterial level. They're incredibly efficient, and this again hopefully gives us some comfort that even though part of the air we have in the cabin is recirculated, it is actually quite clean. Approximately 25% of the cabin air is recirculated on classics, and about 50% on the NG and on the MAX. Now, a common question that you get on the line is, which is it best to do for cooling and ventilation, to have the pack in high or the recirc fan on? Well, the answer is that a pack in high flow will produce more cold air than normal, but it's got a 25% higher bleed air demand. The recirc fan will switch off if either pack is in high flow, and that gives a net reduction in the ventilation rate of 15%. So in actual fact, best cooling is achieved with the packs in auto and the recirc fans on. This also reduces the pack load, bleed air demand and fuel consumption. So bottom line, packs auto, recirc fans on. That's the config that you want. The 731 and 200 didn't have recirc fans, they had instead Gasper fans. It's got a slightly different function. This is an electric fan designed to increase pressure in the Gasper system, which are the outlets above the passenger seats, under conditions of low supply pressure or high cold air demand. So this is normally on the ground on a hot day. The Gasper fan is still effective even if the packs are off, as cabin air is drawn into the distribution ducts down the rise and into the main manifold and mixing chamber It's then blown into the cold air risers and ducts and out of the gasper fan. So it goes through all the aircon system. It just doesn't actually pass through the packs themselves. So the main benefit of this is just to increase airflow. It's not necessarily colder air; it's just an airflow. So it's the equivalent of you having a fan in your hand and blowing yourself with a fan. That's what this is. Ground conditioner. This enters the hatch under the centre of the fuselage, right beneath the mixed manifold. I say I couldn't show it you on the photo of the mixed manifold, but here's it from the outside, and above that is exactly where the mixed manifold lies. A couple of points to remember for those who might have forgotten or newcomers to the 737. First thing is that the temperature controls in the flight deck have got absolutely no effect when using preconditioned air. The temperature you get in the cabin is the temperature at which the air is supplied by the airport. The temperature controls in the flight deck have got no effect because the packs are off. You're not using packs. That's why you've got ground conditioned air. Second point to say is that this air is not the same as external air for engine starting. External air for engine starting is high pressure air, very high pressure air that goes straight into the right pneumatic manifold, and the entrance for that is near the right wing root, and that is covered in the pneumatic section. This ground conditioned air is low pressure, warm or cool air as required to keep the cabin at a bearable temperature when you haven't got an APU. The left and right pneumatic ducts are normally split by the isolation valve, and this is so you've got a level of redundancy in the pneumatic system. If you should have a fault in one side in the left or right pneumatic ducts, and by a fault I guess what I really mean would be a wing body overheat. So there's a leak in the duct or perhaps the smoke in there or something untoward. So if you need to shut off one side, you can do with the isolation valve. Now with the isolation valve switch in auto, which is its normal position, the isolation valve will normally be closed, and you can tell that because you can see a split in the duct pressure. Now the duct pressure split is not normally as large as the one in the photograph, but it's it's usually there. With that isolation valve switch in auto, it will automatically open when either an engine bleed air is switched off or a pack switch is switched off. In that photograph you can see that there is a split in the duct pressures, therefore the isolation valve must be closed. Therefore, although you can't see them, the two pack switches and the two engine bleeds are in auto and on. Equipment cooling. So as we've already said, some cabin air is used to cool the flight deck panels, display units, circuit breaker panels and the E&E bay. Again, just to emphasize the point, the equipment cooling air actually comes from the cabin air. The flight deck air comes directly from the left air conditioning pack along the keel beam and up to the flight deck. So these are two different air supplies. I realise equipment cooling happens in the vicinity of the flight deck, but it is not the same as the air for conditioning the flight deck. You can see on the right the two photographs there. The lower one is that you find on originals, where there was just a single equipment cooling system. So, but on the classics, the NG and the Max, it was split into supply and exhaust, so that there was an extra section added. Now, with the supply and exhaust fans, notice that they're labelled norm and alternate. They are not labelled on and off. There actually is no off position for the fans. What you're looking at here are switches for 4 fans. The supply normal fan, the supply alternate fan, the exhaust normal fan, and the exhaust alternate fan. It's not an on and off. There's a low flow sensor in both the supply system and the exhaust system. If that triggers, the associated off light comes on, and it'll sound the ground crew call horn, which you will hear as that sort of distant buzzing in the background in the flight deck. Just while we've got the picture on the screen, the top picture of the two is taken from the Max, and it's different from the classics and the NGs because it has the equipment smoke caption there as well. I will cover equipment smoke more in the fire protection section. The overboard exhaust valve, this is normally open on the ground and in flight below 2 psi. Above 2 psi, the air, which is now warm from cooling the equipment, it's diverted to the underfloor of the forward cargo hold to help with the heating of that. You will possibly have heard this valve opening in flight. Usually when you're on approach around about 15-20 miles out from the airfield, you will hear a sudden faint hissing sound, and that is the sound of this valve opening. You never seem, or I never seem to hear it closing, but I guess that's because it closes in the climb, and in the climb the flight deck's a lot louder because the engines are obviously at a higher thrust. But certainly on approach you notice it. So next time you hear this hissing sound suddenly occur on the approach, just have a quick look at the cabin diff pressure, and you should see it's around about 2 psi. The overboard exhaust valve will also open if either pack switch is in high and the right recirc fan's off, and this is to give increased ventilation and smoke removal configuration. The forward outflow valve. Now this was only there on the originals and the classics, and it's located on the left hand side of the fuselage, below and aft door 1 left. You can just about see in the photograph there that thing on the top left of the photo. That is the bottom of the air bridge, up against door 1 left, so you can see where it is now, and it acts the same as the overboard exhaust valve. The originals, the 1200 series, had a blue forward outflow close light between the ram door full open lights. That's what that toothless gap is between the ram door full open lights that we've all lived with on the classics and the NGs on the pneumatics panel. Interestingly, the ram door full open lights have now also gone on the Max, so the only surviving light from the originals to the Max is the dual bleed light. And as a further point of trivia, the dual bleed light was not there on the very original specification of the 737. It was just the 3 lights to the right. So there's been quite a lot of evolution on those 4 lights, but there we go. The cargo holds, they are heated by cabin air. The cabin air leaves the cabin through foot level grills, which you will see between the side wall and the floor of the cabin. Next time you're in the cabin, if you haven't noticed them already, just have a look. They're about 1 inch or so wide, and they run the full length of the cabin. So the air goes out of the cabin down through those grills, and it then passes through the sidewall area around the outside of the hold. Now this is important. The holds do not directly get cabin air inside them. And this is for fire suppression and smoke containment reasons. So the holds are heated indirectly by warm air from the cabin passing around the outside of them, not through them. The forward hold, which is actually the one we're looking at here, and you know that now because you can see the mixed manifold there, therefore it must be the forward hold. This has got additional heating from equipment cooling exhaust air in flight above 2 psi when you hear that valve close. The specification of the holes, they're actually designed to, or the forward hole is designed to maintain at least 4.5 centigrade, and the aft hold at least 0 centigrade, at a distance of 8 inches, i.e. beyond 8 inches from the walls and the doors. So the centre of the hold should maintain at least those temperatures, and they'll very often maintain significantly more. It depends on the cold soaking, you know, on the duration of the flight. Quick word about max differences. Well, I guess the main difference is that it's got the long-bodied air conditioning on all of the Max models. Even the short-body Max, the Max 7, has the air conditioning system of the Max 8 and Max 9 and Max 10. This was just for standardization, which reduces production costs. Boeing said, right, you know, we'll just have the one system and it'll do for all. It's got a digital bleed air control system and electronic controller. Again, this is a pneumatics feature, not an air conditioning, but I mention it again for those of you that haven't yet seen the pneumatics module. The big difference here that it's not an all or nothing system as it is on all the previous generations. The digital bleed air system takes just the amount of bleed air that is required to do whatever job is required of it, and that means it takes by and large less bleed air than it would do. Taking less bleed air means more bleed air for the engines, which increases performance, or another way of looking at it, reduces fuel burn. As I've already mentioned, the blue ram door full open lights have been removed, and the bleed trip-off lights have been replaced with bleed lights. Again, they've given them a different name to emphasize that they've got different functionality. This again is a pneumatics subject, not an aircon. You can see the differences there. I've outlined them. The under pressure is the big new one, or a failure in the bleed system, or an incorrect bleed config after takeoff. So that's it for air conditioning. There's quite a lot in that one, and I hope you managed to watch the pneumatics one first. The next one coming down the track will be pressurization. But as ever, if you enjoyed this video, please do me a favour, give it a like, subscribe to my channel. This helps boost visibility of the presentation on YouTube, which all helps the cause. So thank you again for watching, and stay tuned for the next presentation. Thank you.